Okay, so I will proceed to the next topic, which is the next mapping technique. This is the associative mapping, and the next mapping technique is called the direct mapping technique. And what is happening in direct mapping technique? Like in this case, first, in direct mapping technique, instead of storing the total address information with data in cache, like in associative mapping, total address and data uh, both are stored. But here, instead of storing the total address information with data in cache, only the part of the address bits is stored along with the data in the in this technique, part of it. Okay, not the full address with data. Okay, like how? First, we need to divide the address into two form, like into two fields. The lower order m bits is called the index. Okay, 16-bit address is there. Now there's that 16-bit is divided into two fields. One is the lower 8-bit is called the index, and the upper 8 bits 8 bits are called tag. Okay, so the cache memory basically stores the maximum 256 data according to our example, okay, which is given 256 data words, and their associated tags. So due to a miss in the cache, if any miss occurs, then a new word is brought into the cache. The tag bits are stored alongside with the data bits here in this way. The tag bits are stored along with your data. Okay. The index field is used as the address to access the cache. Actually, the index part, that is the lower part of this. This is, suppose this is the main memory. This is the main memory. 64 kilobytes of memory is there. So it is started from 00000 to certain memory address like FFFF. Okay. So this 16-bit is divided into two fields. So lower 16-bit is called the index, which is used here in this case 00. And upper is upper 8-bit 8 bits, these are called tag. So it is given in this position. Okay, so every tag, so tags are stored in this way along with the data, and index are used to access the corresponding word. Okay, so the index field is used as the address to access the cache when the CPU generates a word address. The tag field of the CPU address is matched sequentially with all tag values stored in this cache. Okay. If the CPU's tag address, is matched with any cache tag, that is there is a hit. That means there is a hit if it matches, and the desired data word is read by the processor from the cache. Now, if there is no match, what happened? If there is no match in cache, then there is a miss, and the required word is read from the main memory, which is then stored in the cache together with the with its new tag, replacing the previous tag data pair value, and thus the new tag data pair is placed in same index location. Same index location uh, in cache as CPU's current index of the address for which miss has been occurred. Now, but must be one problem, and due to this new tag data is placed in the same index location in cache. What happened? The hit ratio will drop considerably. Okay, why? Because if two or more words whose addresses have the same index but different tags, and these are accessed repeatedly in your program, then there must be a chance to drop the hit ratio. Okay, now to minimize or to overcome this type of problem, again, this cache is divided into a cache block, and also called the cache lines. A block contains a set of actually contiguous address words of same size. Now each block here, look at this diagram here, the it is this cache is divided into certain blocks. Okay, so there are the cache memory is 256. It can store maximum 256 words. 256 words means 002 ff, because 2 to the power 8, 2 to the power 8 combination means 256. So 002 ff. Now 00 to 07, 8, this 8 index are there to create a block. So how many blocks will be there? Total 32 blocks from block 0 to block 31. Okay, in each block 0, there are 8 index fields, and along with 8 at the same tag, because 0000, then 0001, then 0002, then 0004, then 00056, and all the way up to 0007, and then it will be 0108, then 0109. So in this way 010f, and all the way up to 02, means 20ff, that will be the maximum location. Okay, so the address, 16-bit address into divided into two parts. One is the index part, lower 8-bit is your index part, and upper 8-bit is your tag part. And in cache memory, both tag and data are stored in this way. Now the index field is now divided into two parts. Here also index field is divided two parts, and one is the block field and another is the word field. Block and word. Okay, so 8 bits are again divided into two fields. One is the lower 8 bit is called, lower 3 bits are called word, upper 5 bits are called block, and the combinations of these two fields creates an index. Okay, so since each block size is 8 words, the 256 word cache can hold 32 blocks here, 32 blocks. And a word within a block is specified by 3 bits. Okay, so 32 blocks are there, and a word within a block is specified by 3 bits. Since each block, so 5-bit is called field. So 5-bit field, uh, the block number is specified with a 5-bit field, since there are 32 blocks, and a word within a block is specified by 3 bits, since each block contains 8 words. The tag field for all stored word, that these are the tag field for all stored words within a block is same. Since a block contains consecutive 8 words of data, when a miss occurs in cache, an entire block must be brought into cache memory from main memory. The entire block we call from the main memory. Like in this case here, the whole block from 00000 to certain means the 8 consecutive locations. The full block will be copied from main memory to cache memory here. Okay, so if it is there, then because each index is different, so what will be the tag of this? No problem, same index is not there for every tag, for every location here, for every block. The indexes are different from one another, so that hit ratio must be increased. It will not drop anyway. Okay, so there are certain advantages, like this is the simplest type of cache mapping, since only the tag field is required to match, and that's why it is one of the fastest cache. Okay, and also it is less expensive cache relative to the associative mapping, because instead of storing all 16 bits of the address, only tag value of 8 bits is stored along with the data word. Okay, but there are certain disadvantages as well. The hit ratio is not so good. It needs frequent replacement for data tag value, because there is fixed cache location for any given block. For example, if a program happens to reference the words repeatedly from two different blocks that map into the same cache block, then the blocks needs to be swapped in continuously, making hit ratio to drop. Okay, that is the disadvantage. And next is the set associative mapping cache. Here what happened, this actually the direct in direct mapping, cache can hold maximum 256 words according to the example. The set associative cache is an improved version of direct map cache organization, where multiple of 256 words can be stored, but with increased cost. In set associative cache memory, two or more words can be stored under the same index address. Like in this case, two or more words data, same index address. Okay, so it's a one type of setting, two-way set cache memory. So here index is same, but within one single index, two different type of tags are available. One is 00, another is 01. Okay, so for every index, like for 01 also, the tags will be different, same index but tags will be different. For 02 also, for 03 in this way. For ff also, there has been some two tags like 02 and 01. Okay, so two tags are in the same index field, and that's why uh, the number of tag data words under an index is said to form a set. Okay, so it creates a set. Now assume if k number of words with their associated tags are stored under an index of cache, then the cache memory is called k-way set associative memory. Like here in this case, we have set size of two numbers. That's why it is called the two-way set associative cache memory. Two numbers has been loaded into the same index. Okay, so two tags have been loaded inside one index. So that's what is called the two-way set associative cache memory. Okay, so this actually the advantage is this cache memory has the highest hit ratio compared to the other two cache mappings, and a disadvantage is this is the most expensive memory because cost increases as set size increase. There may be two-way set, there may be three-way, four-way set. So if you increased your set numbers, the cost will be increased, because to store inside this cache memory you have very large amount of space. So there are two replacement algorithms by which we can uh, replace the old data with the new one. And first one is the FIFO, which is first in first out algorithm. And in this algorithm, what happens? This algorithm actually used to choose the word that has been in the cache for a long time. Okay, so that means the word which entered the cache first, that will be uh, pushed out first. Okay, first in first out. Okay, so suppose any word which is not used in a recent time by the processor, so that data should be replaced by the new data. And if so that data is already stored in very long uh, time before, so that's why it is in first in first out, that will be first in and it will be replaced by the new one. And least, the next method is, second method is least recently used algorithm. That means the algorithm, in this algorithm what happened, it is used to choose the item for replacement that has been used by the CPU minimum number of times in the recent past. Okay, so actually here it has been used by the CPU that minimum number of times those data bytes or instructions, whatever the information is used by the CPU, that will be replaced first, then the uh, next one. Okay, so that is least recently used, which is used recently, a very less number of times, that will be replaced, that must be replaced by the new one. Okay, so there are two replacement algorithms. So there are cache types are available, depends on the two parameters. One is the kind of information they can store, and another is the level that occupy in the memory hierarchy level. Okay, so according to the first parameter, which is the kind of information they can store, is instruction cache, data cache, unified cache, and split cache. So instruction cache or I cache, data cache or D cache, where instruction cache is it is used to store only the instructions, Okay, while data or D cache stores data only. Okay? Unified cache, the use of this one is both this cache that stores both instructions and data. That is called unified cache. And split cache consists of two associated but largely independent units, and I cache for instruction and D cache for data. The two I cache and D cache both are present, but these are associated but largely independent unit. Okay, largely independent unit, and that's what is called split cache. And based on the level of memory hierarchy, there are two cache which is called level 1. Primarily there are two caches, level 1 or primary cache, and level 2 which is secondary cache. Now based on the OS or the advancement of the processor, if there has been many more number of level, you can increase the level according to your requirement. Okay, so L1 and L2. Now early computers employed a single multi-chip cache that occupied one level of the hierarchy between the CPU and the main memory. Two developments made it desirable to introduce two or more cache levels in high performance systems. Okay, now the feasibility of including part of the real memory space on a microprocessor chip and growth in the size of main memory in typical computers. A level 1 or primary cache is an efficient way to implement an on-chip memory. An additional memory level can be introduced via an off-chip. Now, on-chip means it must be fabricated along with the processor in the same board or same item, using the same technology. And level 2 means that is off chip, means it is not within this processor chip, it is outside of the processor chip is included. Okay, so that is the level 2 or the secondary cache. So these are actually about the cache memory. Next is the virtual memory. Okay, so do you have any queries? Do you have any queries? Do you have any queries, any doubts?
Sir, nowadays for modern processor, which cache mapping technique is used?
Sorry, can't hear your voice.
So nowadays for modern processor, which cache mapping technique is used?
So it based on your requirement like L1, L2, L3. this type of cache, and according to your budget, according to the compatible of the hardware and software level, maybe set associative, maybe direct, or maybe associative mapping can be used. It's not mandatory that always you need to use the associative mapping. It is not mandatory that always you need to implement the direct mapping. Okay, so different types of computers are available of different budgets. So according to your budget, you need to select the corresponding hardware and software packages.
So is there any speed matter in this case?
Yes, always. Always. Okay, anyone else?
So that means the mapping technique is not fixed by the processor itself.
No,
We can change it.
not you can. When you need to build up a system, okay, so you have to design your system. You need to remember these kind of things. So according to your budget, according to your requirement, you can set the corresponding system components.
Okay, sir.
Okay, so anyone have any doubt, any queries? If you don't have any doubts, I will go to the next section, which is called the virtual memory. Okay, so let's start the virtual memory. Now, what is virtual memory? A memory that is hardware that your computer uses, the load uses to load the operating systems and run different types of programs. Now, every computer needs one or more RAM chips that according to its requirement, and each have several memory modules. Okay, the amount of memory, it is limited, like 1 GB, 2 GB, 4 GB, in this way. So because your computer has a finite amount of RAM, it is possible to run out of memory when too many programs are running at one time. That is multi-programming. Okay, so multi-programming, at that time, maybe your system, it is running very slowly. Okay, if you have opened several number of, if you have load several number of softwares, like as for example, suppose in your desktop or laptop you have installed more number of softwares which needs a maximum number of spaces. If your RAM is occupied by these softwares or any applications or any programs, and within a due time, then your system may be slow. You can't operate at a time 3 or 4 things. Okay, means you have to uh, perform one application, you have to execute one application, then minimize it and open another application. So it takes much more time. Okay. So this is where your virtual memory comes in. Okay, so the virtual memory actually increases the availability of memory of your system by enlarging the address space or places in memory where data can be stored. Okay, it does this by using hard disk space for additional memory allocation. However, since the hard drive is much slower than the RAM, because it's a secondary memory, data stored in virtual memory must be mapped back to real memory in order to be used. Okay, okay, so I have 9 minutes. After, if this discussion ended, not ended within 8 or 9 minutes, I need few more times. Okay, so you have to click on the same link so that we can continue the up to the last one. So it must be, so actually what is done, a virtual memory is a technique, it is a technique used in some computer which gives the programmer an illusion of having a large main memory, although which may not be the case. Okay, it is just an illusion. So there is no actually existence of the virtual memory. It's a technique. Okay, it's a technique, it's a concept. Okay, so physically there is no virtual memory, physical existence is not there. So it's an illusion of your main memory. Okay, it is an illusion of your main memory. So in using this technique, your memory can be divided or separated in such way that it looks like you have very large number of or extra memory capacity, but it is not actually so. That it's a technique or it's a concept. Now how can you implement this technique, that we'll discuss here. So each program has its own address space, which is broken up into pages. Okay, broken up into pages. So each page is a contiguous range of addresses. Now these pages are mapped onto the physical memory, but to run the program, all pages are not required to be present in the physical memory. Okay, so you're actually the now what happened? The size of the virtual memory is equivalent to the size of the secondary memory. It's very less. Each address referenced by the CPU, called the virtual address, is mapped to a physical address in the main memory. Now virtual memory address is called the virtual address, and main memory addresses are called physical addresses. Okay, physical addresses. So your program, which is now these suppose this is your program, it is divided into certain pages. Okay, certain pages. So these are called page, and in the same way in your main memory is divided into certain frames. So each page is equivalent to the each frame. Here each page is equivalent to the each frame. So here certain if one program is loaded inside the virtual memory, this program is divided into certain pages, and if these pages are stored inside RAM, inside your hard disk, so that can be mapped in such way it is easily stored and easily accessible by the processor. Okay, so if you don't have the larger memory space, you need to create a virtual memory where your virtual memory space is divided into page frames, pages, and your main memory, the physical memory, actually these are the physical addresses. Every addresses are called physical address inside this main memory in RAM. So virtual memory works fine in a multi-programming system with bits and pieces of many programs in memory at once. Okay, so that is used for multi-programming purpose. Now, what is the first understanding the logical address or virtual address and the physical address. Now, logical address is generated by the CPU while a program is running. The logical address is a virtual address as it does not exist physically, therefore it is also known as virtual address. Okay, so physical address identifies a physical location of required data in a main memory. The user never directly deals with the physical addresses but can access by its corresponding logical addresses. So your physical addresses are stored situated inside the main memory. Your virtual addresses are stored inside the virtual memory. The hardware device which is called memory management unit, MMU, is used for mapping, or it is used for converting the logical address to its corresponding physical address. Okay, so there must be some logical address. Using that logical address, the actual physical address must be identified. So here, how the logical address must be given, it's a simple MMU arrangement. Memory management unit is there. So this is the CPU and this is the main memory. in between there is a mapping hardware circuit which is called the memory management unit, which is used to convert or map the logical address into physical address. Suppose logical address in this case, a special register is used, or its register is called the relocation register, which is implemented inside the MMU unit. The content of the relocation register is added to every logical addresses generated by the user program at the beginning of execution. For example, if the here in this case, if the relocation register is 2000, relocation register holds an address value 2000, then a reference to the location 0 by the user is dynamically relocated to 2000 address. A reference to the address 150 is mapped to the address and it is converted into 2150. So this 2000 is mapped with this logical address 150, so that your physical address must be generated, and using this physical address the corresponding data byte can be accessed. Okay, so you have created a virtual address, and with using that virtual address and one memory and the relocation register address, physical address must be generated. Okay, so there are two techniques by which the virtual memory can be implemented, can be processed. One is called the paging, another is called the segmentation. And so paging, what is this? Paging actually a storage mechanism which is used to retrieve the processes from the secondary storage, maybe hard disk, into the main memory in the form of pages. Now the main idea behind this paging is to divide each process in the form of pages. One program is divided into different pages. The main memory will also be divided in the form of frames. So if your RAM locations means if one program, one application is stored inside your RAM, that program should be, or that application should be divided into certain frames. And if you want to store it inside virtual memory, take it into a virtual memory, then your virtual memory, this pages, the virtual memories are divided into certain pages, so that your page must be equal with the frame. So the size of, so pages of the process are brought into the main memory only when they are required, otherwise they reside in the secondary memory. You don't need to restore it. The size of the each frame must be equal with the pages. So considering the fact that the pages are mapped to the frames in paging, page size needs to be same as frame size. Okay, now different operating system defines different frame sizes. So here CPU gives the logical address, where your addresses are divided into two forms. One is it is the pages, called the pages, and the the displacement or offset, it is called the offset. Okay, so each address generated by the CPU, it is divided into two parts, the page number and the offset number. This is P means the page number and D means the offset or displacement. P, the page number P, it is page number P, it is used as index in the page table,